Yes, welcome back to Easy Gates Gate 22 Electrical Solutions. The next problem also based on control systems, a second order control system. Very interesting problem. Connected to little bit of AC circuits analysis also, something like how we played in AC circuits. So this is the given problem. We have an LTA system having a transfer function G of S that is given as 100 by S square plus 0.1 S plus 10. That has static sensitivity K, omega n square and damping hidden. Okay, we'll find that. Then the problem is the steady state output of the system to the given input command R of t is given as Y of t. So Y of t is given as A plus B sine 10t plus theta, and input is also given, that is 1 plus 0.1 sine 10t. Okay, so problem is the given system is allowed to reach steady state, and then we need to comment on the output. Then how to approach this problem? Okay, we'll see. So given input is 1 plus 0.1 sine 10t. Exactly speaking, this is a DC component. With respect to circuit analysis, this is the AC component. So we have an excitation for a second order system. It may be an RLC circuit also behaving like this. Okay, right? So simply it is given as a second order system. Okay, it's up to you whether we go by a system perspective or based on the control system perspective, circuit perspective or control system perspective. It's up to us. Let me take this as a DC component and this is a AC component. This is a constant. Okay, so I'm calling it as a DC. Then this is the instantaneous time varying. I call it as a AC component. So you feel like a system excited by or a circuit excited by a DC plus AC. What we do is actually to get the response, output response, we usually go for a superposition. Yes, you can happily apply the or bring the superposition into the play. So activate DC alone and see how the second order system is reacting. Activate AC alone and see how the second order system is reacting. Then add the two responses. Okay, you will get the final steady state output response as expected by the designer. An output expected response is given. What is the expected output response? If this is the input command under the steady state, this is your output. That means in the output, what we have is we have a DC component, we have a AC component. In the output, A is a DC component, B sine 10t plus theta is the output component. Okay, so this is the AC component in the output. So what is A? It's an overall final value. Okay, for the DC excitation. What about B? It's only the amplitude of your output for the given AC signal. Okay, so let us split the problem into two parts. We'll play in the DC and we'll play in the AC. We'll get the response. First, we'll try to get A. That's easy because that's a DC response. If that alone is matching, for example, A equal to 1, A equal to 1, A equal to 10, A equal to 100 given. Suppose if we get luckily A is equal to 10 or A is equal to 100, the problem is over there itself. For a simple verification sake, we'll find the B as well. Okay, so that's how, okay, we can approach this problem. So what is given in the given transfer function? Okay, it is in the form of K into omega n square by A square plus 2 zeta omega n s plus omega n square. Okay, so compare this. So what is omega n square? When you compare these two, omega n square is going to become 10, omega n square is 10, and K into omega n square is equal to 100. Therefore, K is equal to 100 by omega n square, or you can let S equal to 0 in this, and whatever you get, that's a K. By habit, you can do that. So there is going to be omega n square is 10. So the static sensitivity of the second order system is going to be 10. So omega n is equal to root 10 radian per second. Okay, and 2 zeta omega n, 2 zeta omega n is given, that is 0.1. So 2 zeta omega n itself is equal to 0.1, means zeta will be definitely less than 1. It's going to be a underdamped second order. Yes, we are playing with the underdamped second order. Now let me take a simple underdamped second order. So if it has K into omega n square, the whole divided by A square plus 2 zeta or eta omega ns plus omega n square. And this system is excited by a step input, that's like a DC. Okay, so this is the input. What is the input given? Input given is 1. So let me treat this as a It's applied at time t equal to 0 second. That's a DC. Then what will happen to this output? This is your second order under damped system. So what will be the response? The response will be starting from 0. Then there will be transient oscillation. Then will finally settle to a value called AK. What is A? A is our step size as per the fundamental. Okay. This capital A or magnitude of your step, and K is the static sensitivity of the system. Since the output response is given only at steady state, so then this is Y of t. So for DC input, this is Y of t. For DC input, what is the final value? It is given. So Y of infinity for DC value is known, that is equal to A into K. So the step size is 1. DC is 1 and K is equal to, already we have determined the K is equal to 10. Therefore, the steady state value for DC must be equal to 10. That's your response under steady state. So that means what is given as a steady state value for the DC means that is your A. So A must be equal to, so Y of infinity is given for a DC input as A. If that is the case, A must be equal to 10. So A is equal to 10 means, can we freeze the options? Yes, we can. It is going to be option B only. Okay, but a small confirmation. Okay, so K is, static sensitivity is 10. That's fine. Step size is 1. Yes, definitely it's going to settle at AK only. Okay, that's fine. So let me verify with, yes, I'm expecting B to be equal to 1. We'll see. So let us go for the AC excitation of the same system. K into omega n square by A square plus 2 zeta omega ns plus omega n square. So exciting by AC. So let me take this as A sine omega t, where A is the input amplitude. Okay, that's A, it is plus A, it is minus A. Okay, that's excitation R of t. Then what is the Y of t? Under steady state by using sinusoidal steady state response analysis. By using sinusoidal steady state response analysis, we remember Y of t is equal to A into M. That's your output amplitude into sine omega t plus phi. Okay, where omega is the given frequency of excitation. So this is given. What is given for the AC component? It is given as 0.1 sine 10t. Let me take that component. So this is 0.1 sine 10t. So the input amplitude is equal to 0.1 and omega is equal to 10 radian per second. Okay, a system with omega n is equal to root 10 and damping less than 1 and K is equal to 10 excited by a frequency 10 with an input amplitude 0.1. The question is, what is the output amplitude? Because Y of t is given as what for sinusoidal component? B sine 10t plus theta. Okay, that's how it is mentioned. Okay, but theta is not given, so we need not to find the phi. Let us focus only on the amplitude, output amplitude. How to get this amplitude? So when you have a transfer function T of S, we can let S equal to j omega, it becomes T of j omega. Then we can put T of j omega into polar form. T of j omega in polar form is mod T of j omega for the given frequency and at an angle T of j omega. This is what we call as a magnitude. This is what we call as a phase angle. So that means you set S equal to j omega, put your transfer function to polar form. That will give magnitude and phase angle. That magnitude multiplied by input amplitude will give output amplitude. That magnitude multiplied by input amplitude will give output amplitude. Therefore, the output amplitude is given as B. Therefore, let me take a call. B is equal to the input amplitude into the magnitude. So problem lies in finding only what? Magnitude of your transfer function. So A is already known, that is equal to 0.1. Let us find only the M. Okay. So What is our transfer function? T of S is equal to 100 divided by a square plus 0.1 S plus 10. So let S equal to j omega. So T of j omega is equal to 100 divided by, and that too, what is omega? 10. So therefore S is equal to j omega means I can let straight away S equal to J10. Set S equal to J10. So J10 square is going to become minus 100 plus J10 means it is going to be J1 plus 10 I will get. So this is going to become 100 divided by minus 90 plus J1. We are looking for only the magnitude. Yes, focus on that. So the result is going to be 100 divided by root of 90 square plus 1. So comparing to 90 square, 1 is nothing. Therefore, let me reduce this to approximately 100 by 90. Okay, root of 90 square, 90. Then 100 by this is going to become, okay, that's your M magnitude. Yeah. So what is your B? B is nothing but A into M, input amplitude into the magnitude at this given omega. Okay. So then A is given as 0.1, M is known now, it's 100 by 90, and then 0.1 into 100 will be 10. So it's going to be 10 by 90. So then it will be 1 by 9. Okay. Yes, 1 by 9. Okay. But something like this is not mentioned in the options. Okay. So A is equal to 10, but B is equal to, we are getting 1 by 9, but nobody is matching. Let me confirm A first. 1, A is 10. So AK must be 10. There is no other choice. That's fine. Okay, so amplitude is 0.1 and magnitude is 100. That's fine. So J10 square minus 100 minus 90 square, 100 by 90. Okay. Okay, seems to be fine. Seems to be fine. There may be a mistake committed by the designer. Even if you suspect the second, there is no doubt on the first. Yes, during the examination, you can pass. You can move to the next problem by giving the answer is option B. Okay, that's fine. Okay, so there is a mistake by the designer. B must be 1 by 9. If we are all right. Okay, so in the examination, that's why we need a lot of verification techniques. So you just verify your steps. If you're okay with that, believe, okay, confidently move to the next problem. You didn't commit any mistake, it seems. Okay, so the answer you can pick, probably you pick it during the examination, is A is equal to 10. And looking for B is equal to 1 by 9, that is not there in the options, but still the best possible answer is option B. Okay, so but problem may fall into marks to all also because options are not given correctly. Okay, but still the one should choose option B only during the examination. So the problem is very interesting, exploiting the fundamentals of DC plus AZ, exciting a second order system, a system perspective. So you can take the problem to the control system only. So I approach the problem only in the control way. But since it is a linear system, linear time invariant system, I brought the superposition into the play. So I got the DC response first, and then getting the sinusoidal steady state response. In that only the amplitude is a problem. So we focused only on the amplitude. Suppose if the problem is the phase angle, you know what to do. If the problem is phase angle, if also given, then look for angle of T of j omega. That will also give the necessary clarity. So if phi is given, I should have played with phi instead of the magnitude. Okay, yes. If suppose if magnitude is not mentioned, okay, suppose it is 0.1 into m sin omega t, 10t plus some phase angle given means he may force us only by the phase angle route. Okay, so that's one of the interesting problems in GATE electrical 22 paper, and hope you enjoyed this content, and do subscribe the channel and look for the updates. Okay, yes, we'll update you soon with the next problem.